Yes, spring break is almost upon us. All right, so if you've watched all the Calculus 2 videos I put in the playlist, then good for you. But I know that you guys have not. I mean, there's 10 videos there, right? So chapter 5 in Gamelin is on this treatment of series, power series, really, in the complex setting. So again, I'm skipping straight to section 5.2, and just to give a title for what we're doing right now, we're studying sequences of functions. So if you watch the previous 10 videos I put in the playlist, in there I describe how to treat numerical series. Well, first of all, before that actually, I talk about numerical sequences in the ones I haven't posted for you guys. And then after you're done talking about sequences and the convergence of sequences, you turn to the question of the convergence of series in terms of the limit of the sequence of partial sums. We develop a bunch of convergence, divergence tests for those in Calculus 2, right? Direct comparison, limit comparison, ratio, root test, all that. And then once that's done, we talk about power series, which are really functions which are defined in a very specific way. Like a power series is a function whose formula is given pointwise by a numerical series, all right, with fixed coefficients. And so really to understand power series, you have to study convergence of a sequence of functions. And that's not something that you did in Calculus 2, right? So this is something genuinely new that we're talking about here. And as such, I need to give you a definition. So, because there's a couple different notions of convergence for sequence of functions that we need to distinguish. A sequence of functions, Fn on E, is said to pointwise converge to F if the limit as n goes to infinity of Fn of z is equal to f of z for all z in E. So we're looking here at E as a subset of the complex numbers, right? But that's not entirely true. I'm going to look at E as a subset of the real numbers for my examples which follow, all right? Because I want to explain to you that the concept of pointwise convergence of a function is insufficient to capture the properties that we want for the limit of a function. Like, we would like to be able to say things like, if you take the limit of a sequence of functions of a particular type, then the limit function is also of that type, all right? And that just is not the case if all we have is pointwise convergence. Let me show you some examples of this, all right? So, here we go, example 1. So here I have Fn of x equals to x to the power n for x an element of 0, 1. So I'm thinking of 0, 1 as being the E here, all right? What's the limit? F of x will define to be the limit as n goes to infinity of Fn of x, all right? In other words, the limit as n goes to infinity of x to the n. So I can draw a graph. So here's 0, here's 1, right? And we can graph the different functions here, right? So like, what's F1 look like? What's the graph of F1? The graph of F1 just does what? It's like this, right? This is F1. Because f1 is just y equals x, right? What's f2? f2 is the parabola, right? It's y equals x squared. So f2 would be this guy, right? There's f2. Then you have f3, which is x cubed from 0 to 1, right? So kind of more of the same. Looks like this, right? There's f3. What happens as n goes to infinity here? Right, if you can imagine it, x to the 10th on this scale would look something more like, roughly speaking, I mean, I'm not quite doing it justice, but maybe that would be f100 or something, I don't know, maybe f10, whatever. The point is, what happens as n goes to infinity? You see what's happening? Well, you can prove that this is 0. So this is equal to 0 if x is less than, if 0 is less than x less than 1, right? And what's it equal to if x is equal to 1? What's the limit as n goes to infinity of 1 to the n? It's just what? It's 1, right? To see that, I'm just saying the obvious. Limit as n goes to infinity of 1 to the n is 1, right? And you can kind of anticipate this graphically. See? So what is the case with the, let me just get rid of my f100 here for a second and just say, so what does f look like? F looks like it's constant, right? All the way out to 1, where it then does what? It jumps up to here, right? So what can you tell me about the limit function f? Is it continuous? The limit function f is not continuous, right? But how about the sequence? The sequence of functions. Is each one of these functions continuous? Yeah, certainly x to the n is continuous on 0, 1 for any n. So here's a sequence of functions which pointwise converges to the function f, right? And the limit function is not continuous, despite the fact that every function in the sequence was continuous, right? So pointwise convergence does not necessarily preserve continuity, all right? Another example. Here we have gn of x equal to n squared x 2n minus n squared x and 0. So this is for 0 less than or equal to x less than or equal to less than 1 over n, and 1 over n less than or equal to x less than or equal to 2 over n, and this is 2 over n less than or equal to x less than or equal to 1. All right. And so this is like what it is it's a triangular spike, basically here. We're going something like this. So here's 0, here's 1 over here, and the top of the triangle is at 1 over n, right? This over here is 2 over n. And so this is what the graph of gn of x looks like, right? What's the area bounded here? Yeah, 1/2 base times height. Great. What is that here for this triangle? The base, easy enough, that's, yeah, 2 over n. And what's the height? So the height you can figure out by plugging in the gluing point into either formula. So n squared times, 1 over n, right? So what you got there? 2's be canceling, and so are the n squareds. The area is 1. So the area of each one of the functions in this sequence from 0 to 1 is just 1, right? So in other words, we have the integral from 0 to 1 of gn of x dx is just 1 for each n in the natural numbers, right? So let's put this together here. What do you have as n goes to infinity? What happens with gn of x? Yeah.
The triangle would just get, like, the triangle would just be like a little stick.
Right.
So like 0 and 2 and get closer and closer and closer.
Right. So I mean, what ends up happening is that
The area goes to 0?
yeah, I mean, gn of x. Well, I would say that gn of x goes to 0, but for x in 0 to 1. But on the other hand, what do you have? You have 1 is equal to the limit as n goes to infinity of the integral from 0 to 1 of gn of x dx, right? Because that's 1 for every n. But that's not equal to the integral from 0 to 1 of the limit as n goes to infinity of gn of x, right? Dx, because this is 0. So 1, of course, is not equal to 0. We cannot interchange the integral and the limit here, right? It's not allowed.
Is there like a discontinuity that's at play there?
Well, I don't. Every one of these functions forming gn is itself continuous, and the area is 1. So, I mean, at first glance, it seems like that's a nice sequence of functions. You ought to be able to interchange the integral and the limit, but you can't, because in some sense, the limit is, well, there's something funny going on here, right? I mean, I said it's equal to gn of x is going to 0, but I'd say that's not entirely, that's probably a little bit of a lie. I don't, as n goes to infinity, I'm not sure that that's quite defined, right? Because, well, I guess the 1 over n goes to 0, doesn't it? So it's okay. But my point is that, nevertheless, the limits can't be exchanged. That's weird, in some sense, all right? And then one more example. So these are cautionary examples. What these examples do is try to illustrate to you as quickly as I can what happens in the real case for sequences of functions, because all of these annoyances are going to fade away as we study complex functions, because the convergence of complex functions is much nicer. So here I have fn of x is equal to x to the n over n for n equals to 1, 2, right? And of course, what's the limit as n goes to infinity of fn here? Well, it's equal to 0, right? Because as n goes to infinity, you've got 1 over n going to 0. And if x is just, here x is an element of 0 to 1, so that doesn't blow up to, you know, the x to the n can't compensate the n. So that limit is clearly 0. And, well, I say furthermore, the limit as x goes to a what can you tell me? Limit as x goes to a of x to the n over n, what's it equal to? Well, this is just equal to a to the n over n, right? And that's true for, you know, for a an element 0 to 1, and it'd still be true for a equals to 0 or a equals to 1, provided we replace the limit with the appropriate left or right limit, right? Okay, so what's the point of this? So we have the limit as n goes to infinity of the limit as x goes to a of x to the n over n is equal to the limit as n goes to infinity of a to the n over n, right? Which is equal to 0. And also the limit as x goes to a of the limit as n goes to infinity of x to the n over n is equal to the limit as x goes to a of 0, which is equal to 0. So, well here, this one, we can exchange the order of the limits, right? So this time the limit as x approaches a in the continuous sense, and the limit as n goes to infinity, these limits commute. See that? They can be interchanged. So it seems like there's hope, right? There's hope for a limit of a sequence of continuous functions to be continuous. What about derivatives? What happens with derivatives? So continuing example 3, example 4, if we look at dfn dx, what is it? ddx of what? X to the n over n, which is what? How you differentiate. You remember the power rule? N x to the n minus 1, you guys know that. So what happens to the n and the 1 over n? They cancel, right? So those guys be canceling. And x to the n minus 1. Let's see here. Yeah, x to the n minus 1. But what is that? That's nothing more than the sequence that we studied. That's example 1, right? So essentially this is just example 1. It's almost example 1. And so the limit as n goes to infinity of dfn dx is equal to 0 if 0 is less than or equal to x is less than 1, it's equal to 1 if x is equal to 1, right? And so the limit as x goes to 1 from the right of the limit as n goes to infinity of dfn dx is the limit as x goes to 1 from the left of 0, which is 0. So what's the point? Well, on the other hand, we can take the limit as limit as x goes to 1 from the left of dfn dx, and that will be the limit as x goes to 1 from the left of x to the n minus 1, which is just 1. So as you can see, what does this say? I said, therefore, the limit of the sequence of derivatives is not the derivative of the limit function. So we have the situation, fn is going to f, but dfn dx is not going to df dx. That's what these calculations show. That's kind of annoying, right? You have a convergent sequence of functions which converges to a function, right? And yet the derivative of that sequence does not converge to the derivative of the limit function. Right. Now, so this means we need a better, if we have a better sense of convergence, then we can get out of some of these troubles. So here it is. Let Fn be sequence of functions on E. We say f of n converges uniformly to f if for each epsilon greater than 0, there exists n in the natural numbers such that little n greater than big N implies the absolute value of Fn of x minus f of x is less than epsilon. But here's the catch. This doesn't hold for 1x, it holds for all x in E. And that's the uniformity of the convergence. The difference in pointwise convergence is, instead of saying the quantifier is different. Like for pointwise convergence, you just need to be able to find an n for any given x that gives this estimate. But here, 1n has to work for all x in E. That's the difference between pointwise convergence and uniform convergence. All right, so, and let me just say this. So, theorem or Gamelin's definition, however you want to look at it, I'll say Fj converges uniformly to F if and only if the absolute value of Fj minus Fj of x minus f of x can be shown to be less than or equal to epsilon sub j, where epsilon sub j goes to 0 as j goes to infinity. Gamelin calls epsilon j the worst case estimator of the difference, right? And typically, you know, we can set epsilon j to be the supremum, the sup for x in E of the absolute value of f j of x minus f of x. Now, I say absolute value, but of course, when we put this into practice in complex, that's going to be modulus, right? All right. So, as we look back at our examples from today so far, right? So, for example 1, what would the supremum of x an element of 0 to 1 such that we're looking at x to the n minus f of x? So here I'm saying f of x is the limit function, the function to which xn pointwise converged. So if you look at example 1, what's the biggest that difference can be? We saw it back in our graphs, right? It happens at 1. The worst that can be is 1. So this is 1. That's what you need for us to make your worst case estimator, epsilon sub n in my current notation. So example 1 is not uniformly convergent on 0, 1. The worst case estimator is 1. It does not go to 0 as n goes to infinity. not uniformly convergent. For example 3, what do we have? If we look at the supremum of x in 0 to 1 of the absolute value of, gn of x minus g of x, so calling g the function to which gn of x pointwise converges. Let's see here. So if you look at the graphs of those tenths, we figured out that the height was 1 over n, right? So let me just use some color coding here. The gn, so like, here's the graph of gn. What's the graph of the limit function g? What's the graph of the limit function g for this one? The graph of the limit function, for example, I said example 3, I meant example 2, right? This is example 2. Yeah, exactly. The limit function, g of x, as we're calling it, is just identically 0. So it looks like this, right? So there's your y equals g of x. To calculate the worst case estimator, we're looking for the supremum, right? Which you can think of roughly as the maximum, right? As a sort of a more intuitive word for that. You have to understand, if the maximum gets numbers arbitrarily close to 1, but it doesn't actually get to 1, that means the supremum is 1. Maximums have to be attained, supremums just have to be approached. So the supremum, right, the maximum difference between the limit function, the red one, and the sequence function, gn, is right here. 0 to, looks like 1 over n, I think. Did I do that right? Oh, wait a minute. My bad. What was the height? That height is not 1 over n. What is it at? This was the height, right? That's exactly, that's n. So my bad. So, I mean, I did it right, but I just interpreted it wrong here. So my point to you is that the worst case estimator for example 2 is n. So in this case, n is the worst case estimator. What happens as n goes to infinity for n? It's infinity, right? So definitely example 2, again, is not uniformly convergent.
When we have the second line, that 1 over n.
Because that's the formula right here.
Yeah.
Well, this one. So these match up. So I just was using the fact that this is continuous, and I was plugging it into that one because it's easier to think through. But if you plug in 1 over n into this formula, you get 2 over n. You get 2n minus n squared times 1 over n, which is 2n minus n, which is still n. But yeah. But anyway, example 2, not uniformly convergent. Example 3, what's the worst case estimator for that one? So there we had, if we look at the supremum from x to 0 to 1 of the absolute value of, what was it? Fn of x minus f of x. This, of course, is a different fn than example 1. What was the deal there? Well, there, if you look at it, the largest the difference is actually 1 over n. So that's the worst case estimator in this case, which of course goes to 0. Thus, example 3 had uniform convergence. In other words, the sequence that we examined in example 3 was a uniformly convergent sequence of functions. Now, to convince yourself that the worst case estimator is 1 over n, we should carefully graph, right, the the limit function as well as the sequence, like a typical function in the sequence, and see that 1 over n is the biggest difference. But I'm going to move on here. You can do that, okay? Okay, so it's not an accident that first of all, we are able to interchange limits in example 3. And also, another way to look at this is that the limit function here, the fn which this converged to, was also continuous. So the limit of a uniformly convergent sequence of continuous functions is, again, continuous. As we've seen, pointwise convergence does not give us that. So here's a theorem, which I guess I should probably put over here. Theorem. If fj is complex valued sequence of uniformly convergent functions on E, and if each fj is continuous and fj converges to f on E, then f is continuous on E. Did you move it? Oh, thanks. So, here's the proof. So, by uniform convergence, there exists n in the natural numbers such that the modulus of fn of z minus f of z is less than epsilon over 3. But by continuity of fn at z equals to a, there exists a delta greater than 0 such that 0 less than modulus of z minus a less than delta implies that the modulus of fn of z minus fn of a is less than epsilon over 3. All right. So I say we claim that f of z is continuous at z equals to a by the same choice of delta. Okay, so consider for 0 less than z minus a less than delta, we have the modulus of f of z minus f of a, all right, is equal to, now this is a little bit tricky, but just adding 0, okay? So we take f of z minus fn of z plus fn of z minus fn of a plus fn of a and then minus f of a. So I added 0 twice, okay? And then triangle inequality. So triangle inequality gives me that this is f of z minus fn of z plus the absolute value of fn of z minus fn of a plus the modulus of fn of a minus f of a. All right, so let's think through this here. Now, since 0 is less than z minus a is less than delta, we have that fn of z minus fn of a is less than epsilon over 3, right? So how about the first one? As long as, so n is, remember n is such that what? This is less than epsilon over 3, right? So that's the first one. And let's see here. So this is less than epsilon over 3 plus epsilon over 3 plus epsilon over 3, which is, of course, epsilon. Now I say where I have used star star for the middle term and the left and rightmost terms, and star for the left. So one of these, the leftmost, okay, so, yeah. This guy right here, right, gives us this, right? So that's true. Huh. Well, let me erase my color coding here. Let's see here. So I think the middle one is from this, right? And okay, so I think this, right, in the case, look at this. So like this holds for any z that's between, that satisfies this condition, right? So over here, if we put z equals to a, that's definitely satisfying. Wait, well, doesn't satisfy that condition. I'm sorry, I'm too close to it today, but other days this has been totally obvious to me. I'm missing something at the moment, just me. Yeah, maybe I regrouped it.
Like you don't put the A's together, you put everyone with the Z and A.
Is that what I did?
I'm just spitballing.
Hmm.
That would give you the Z minus A condition.
Yeah, maybe I need to group. Yeah. Thank you. So like, thank you. I think that's exactly it. I think that's what I think my notes have a typo here actually. So, what idiot wrote these notes? So if I put an A here instead and put a Z over here then to be fair, right? Then I think we're on track here.
You gotta change the middle term to a plus though.
Ooh, I don't want that.
Yeah, where'd you get the second FNA? You know what I'm saying? Get 2 minus FNA.
Do I though?
Yeah.
I mean, I'm saying take this guy with this one to give me that.
Yep.
And this one with this one to give me that. And then see, well, the tricky thing is that this is, we can put a minus here, right? And a plus here, but because we're inside the, I see what you're saying, but because we're inside the absolute value, we can pull the minus out and change it to what I had. You know, modulus of, you know, so, and then if we have this n and we have this delta, we get all three of these are bounded by epsilon over 3, epsilon over 3, epsilon over 3. So there's this, the fact that we have uniform continuity allows us to use that one choice of n for the whole range, which allows you to make this argument. And the thing is, I've said this for complex, but this is still true in what's called a metric space. A metric space is an abstract set with a notion of distance. And you can study uniform convergence of functions on a metric space, and this theorem is still true. It's not really a complex analysis thing, this right here. Okay? Okay, so moving on here. And yet, of course, example 4 is a warning that even though example 3 is a nice sequence, it's a uniformly convergent sequence, its derivative is not, as it happens. So this brings us to the next theorem, which is sorry, if I knew it was good for me, I would have skipped that proof, but if I skip too many, then things stop making sense. I don't know. Theorem 5.29. Let gamma be piecewise smooth curve, and fj continuous converging uniformly to f, all right, on gamma, then the integral over gamma of fj of z dz is equal to the integral over gamma of f of z dz. All right. And what I'm saying here, if you write the limits out explicitly, is I'm really saying you can exchange the order of the limits. See, this is saying that the integral, how to say this? Well, I lost something here. This converges to that, so I'm missing a limit right here. Limit as j goes to infinity. Sorry about that. So to be more explicit, what we're saying is the limit as j goes to infinity of the integral of the fjth sequence function, right, is equal to the integral of the limit as j goes to infinity of fj of z. So you can exchange the integral and the limit for a uniformly convergent sequence of functions. And the proof for this is actually quite fun. I would say more fun than the previous one. The proof is essentially just by the ML theorem. And so notice that we can let epsilon j be worst case estimator for f of j minus f on gamma. That is the modulus of f of z, well, fj of z rather. Come on. Fj of z minus f of z is less than or equal to epsilon j, and that goes to 0, right, as j goes to infinity for each z and gamma. Then what do we have? The modulus of the integral over gamma of fj of z minus f of z dz, right, is less than or equal to what? So this is less than or equal to the integral over gamma, right? Well, excuse me, let me get to the point here. So let L be the length of the curve, right? So this is less than or equal to the length of gamma times the bound. What is the bound for the integral here? It's the worst case estimator, right? So epsilon sub j serves as an m, if you will, for the ML theorem for every j. And that does what? Well, that goes to 0 as j goes to infinity, right? Thus, the limit as j goes to infinity of the integral over gamma of fj of z minus f of z dz is equal to 0. And from that, we immediately get this result up here, right? So the theorem follows from that. Okay, so, all right. So that brings us here at the very end of class to finally get to the material on series of functions, all right? So I forget how much time it takes to really put this all out on the table, but I think it's important for us to do this to appreciate what's going on. I am now hopelessly behind the schedule I've announced in Blackboard. Surprise, surprise. So what would a series of functions be? If you have a sequence of functions, how would you build the series?
How would I build a series?
Right, the series. What? Add them up, yeah. Exactly. So that's what we're going to start with next time, is that we build a series of functions from adding together a sequence, right? And what we're going to see is that you can test for convergence of a series of functions if you can find a numerical series which dominates it. So like if you want to analyze a series of complex functions converging, if you can find a numerical series who is convergent, right, let's say, and the modulus of the series of functions we're looking at is always bounded by that numerical series, term by term, then Weierstrass's m-test says that, guess what, that series of functions converges, and it not just converges, it converges uniformly. It converges uniformly on E. That's our theorem 5.211, the Weierstrass m-test. And then once we have that, we'll turn and we'll have theorem. The next theorem says that a sequence of holomorphic functions on a domain D that converge uniformly to F, then F is holomorphic. So we actually, unlike example 3 going to example 4, where we lost differentiability of the limit, we're going to see that in the complex case, you can't lose complex differentiability of limit. If you have, a sequence of complex differentiable functions that converges, then you get complex differentiability of the limit function. And this is proved using arguments. I see Moreira's theorem in use here, right? Anyway, so it gets a little technical here. I think I might, anyway. So we have, another 30 minutes at least, probably, of this before we get to power series. So power series then are just a straightforward application of the theory I'm developing right now. I think I'm going to make a little video to go through the next stretch, just because otherwise it's hopeless. And so I'm sorry for that, but I blame Audric. You were watching my videos this morning, so it must be your fault.
Corrected you.
You corrected me? Yeah. Oh, well, thank you for that. I do appreciate that.